Database query optimizers have a lot of decisions to make. Should they probe an index? Should they scan? In what order? Should they assign multiple workers to help out? And many others. Sometimes it makes sense to scan an index, although the cost for that grows rapidly. At other times, and very soon, it makes sense to scan. And that decision boundary is called the access path. Finding the optimal path is not as easy as it sounds. It takes years of research, as this paper shows. And then once we do find the optimal path, it takes a long time for it to trickle down into the optimizer. As this diagram shows, the true ideal path is way down here, and the optimizer thinks it's here. What if there was a better way? What if we could use neural networks to try to find the ideal line? And that ideal line changes on different systems and in different queries. First, we'll have to start with some data. We're going to use a TPC-H benchmark. TPC is a non-profit organization that develops benchmarks for data systems. The TPC-H is a decision support benchmark, which includes ad hoc queries, a database model, and some information on how to implement it. We're going to use that to generate our data, and we're going to generate the line item table. By default, one scale factor is 6 million rows, so we're going to generate a scale factor of 10, giving us 60 million rows. And we'll be especially interested in these 5 columns. We'll create indexes on these. The reason we chose these columns is that they are uniformly distributed, so we can predictably step them up and make sure that we have a range of selectivity in various increments. In order to make an effective neural network, we're going to need a lot of data. So we're going to generate samples on 3 different EC2 instances: a general system, a memory optimized, and a CPU optimized system. And we'll create about 25,000 queries that will run against this to give us data points. Let's take this query as an example. Let's look at the extended price portion of the predicate. We'll first encode whether the extended price was used or not. Then we'll take 75,000 as a value. We'll say that it's first in the sequence, and then we'll describe the operation by one-hot encoding it. Less than, greater than, equals, and so forth. Then we'll do the same thing for the next operation in the predicate, the supplier key. And we'll do the same thing for the part key, increasing the sequence that they are in. And any columns that do not participate in this query will just have 0 values. Then we'll concatenate all these vectors and we'll just call it predicate feature vector. We also need to know the state of the system, for example, which columns have indexes on them. And when we run these, we'll put indexes on these columns sequentially to kind of see how the system behaves. And we'll call that the system feature vector. Finally, we need to know a little bit about the machine that this is running on. For instance, because we know hardware does affect the system, it might be valuable to know how many gigabytes of memory are available to the system, how many cores are in the processor, its clock speed, how many kilobytes are available to the level 1 cache for data and for instructions, is the system NUMA aware, and does it have the advanced vector extensions from Intel? Does it also implement self-snoop, and many other things? Those just might be important to the way that the system is able to make decisions on how it uses its memory. We'll call these collectively the hardware vector. We'll take all of these together, and that will give us 84 features to feed into our network. What about our network architecture? This paper describes a similar approach, where they found some success alternating between ReLU and linear activation layers. I tested 10 different network architectures, varying the number of neurons per layer, the number of layers, the different activation functions, and using regularization or not. And I settled on this. Here, every other layer is a ReLU activation. The first layer is our 84 dimension input vector, then 228 dimensional vectors hidden in the first 2 hidden layers, then 64 in the next 2, and then again 2 128 neuron layers, and finally one last layer that gives us a latency computation prediction. This diagram actually is a scaled down version of it. The full version looks like this. Before we continue, it's important to note that the ReLU function has an interesting property. It pushes the negative weights towards 0, therefore keeping them relevant and preventing them from running off into negative infinity. First, we're going to need to install our prerequisites. You can download Python 3 for Mac here and run the package. Then the rest of these can be run using the Python package installer or pip. TensorFlow can also be installed that way, but you only get the CPU only version. If you want the GPU version, you're going to have to build it yourself from source. Now that we got that done, let's get to work building the model. We'll start by importing Pandas and TensorFlow. We're going to do a little bit of data cleanup. As I mentioned, the raw files are already recorded. You can do that yourself if you want to, but I've already provided them here. This is an example of a file from one of the servers, the compute optimized. You can see that there are some categorical values and there are some values that are numerical. And also you can see that our latency is our predicted value or label. But it's still not where we want it to be. So I've already pre-cleaned up one of the files and combined them all. And this is the this is the combined file. And you'll see now we've got some more categorical values, but we've got some NANs and some things we're going to have to deal with. But this is all three of the servers combined. Again, that's provided for us. And then this is what it looks like, one-hot encoded. There's still a little bit of work we'll have to do, but this is the one-hot encoding that we discussed earlier. So for the most part, this is the raw data file. There's also another file included called control for each of the servers. This shows us what the optimizer sees. So this was a separate run that let the optimizer run free to do whatever it wanted. And that's going to be really helpful for us to compare our results to, because after all, we're trying to see if we can beat the optimizer. Now we've got some helper functions here. Some are going to help us plot, but of interest is this find best and find worst. They're going to find the fastest time in each selectivity and the slowest time in each selectivity, and we're going to be using those a lot. So let's build some intuition. We'll start by reading in our control group of what our optimizer thought it saw. And then we're going to clean up some of the columns. For instance, we rename info query ID to match all the other data. Now that we've got that, we're going to compute our fastest and slowest times. And we want that for each of the servers. Now let's see how it compares the optimizer to the fastest and the slowest times. We can see that the optimizer usually sits somewhere in the middle, and at times it touches the worst possible times, but rarely does it match the best possible time. And in fact, if you look at the scale of some of these, it might look like it's closer than it actually is, considering how bad the worst times are. So the optimizer overall is not doing a great job. Now let's compare the three different servers to see, is there a difference in what should be the fastest time on each of the machines? In other words, does the hardware actually matter? And we can see that it definitely does. Sometimes it should be a completely different decision path, and other times the decision just moves slightly one way or the other, being sensitive to selectivity. That could be an effect of the hardware's ability to move stuff into memory into RAM. And so a memory optimized system and a CPU optimized system would effectively behave a little differently if they had different capabilities, but really only slightly. Now let's compare the optimizer to see, did it see differences on these machines? In other words, did it behave differently? Now one thing you'll notice is that the shapes look all identical. In other words, the optimizer is always making the same decision. And you can see that there are consequences. Each of the machines responds differently. That tells us that the optimizer isn't really taking into account what's on the machine, and it's doing a really poor job in paying the consequences for it. So there's a little bit of work that we could do there. So let's get to modeling. We'll take a look at the data, and as we said, we got to do a little bit of cleanup, and there's also all these informational columns, like the name of the EC2 machine that we don't really need because we encoded the hardware features. So we'll take all those out, and we'll only include the ones we want. That has 67 categorical columns. And we'll add in these hardware columns as well, but those need to be normalized because remember, CPU clock cycles were like 3100. So we'll normalize all those, and now we should have 80 columns. So we have an 80 column feature space. Now we want to be able to reverse this. So let's record our latency, which will be our label. And we want to be able to reverse the label to be able to see the prediction and interpret it, if we're going to normalize that too. So we'll save this highest value. Now we'll import Keras and we'll start building our model. It's going to be a sequential model, and as we mentioned, there are going to be 7 layers. There's really an input layer as well, but Keras kind of handles that for us. It will automatically turn our 80 into a 128. Feed the 80 into 128. Then we'll compile it. We're going to use mean squared error as our loss, and we're going to use MAE just to kind of display it because that's a little easier to interpret visually anyway, because you don't have to take the square root. But then again, remember that we normalized the values, so they might not make as much sense till we convert them back. And we'll train this on 100 epochs. Now we sped this up a little bit, but still it was pretty fast at 1 second per epoch. Now that that's done, we can take a look at our model, and it's as we expected. Let's do a quick evaluation of the model just to see what we have. And unfortunately, that doesn't tell us much because remember, we normalized the values. We'll fix that in a second. But let's plot it. At least that'll give us some idea of how the model worked. And this is how the model trained. We see our MSE and our MAE are slowly moving towards 0. Our validation set was always fairly good. So now let's do the work of reversing our predictions so that we can read them. So if we were to look at the models and see what they might have looked like. Let's take a look at what the predictions look like. We expect not to be able to read them. Yep. Now let's convert them back, and then we should be able to get a good idea of what these look like in milliseconds. So these are the predictions in milliseconds. So we have 8.5 seconds on that particular prediction. Okay, great. Now let's see if we can compare them to what they looked like. So let's find the best predicted, in other words, what the model thinks that the fastest time should be, and let's compare that to the actual true fastest, and also to what the optimizer thinks the correct path is. If you look closely, you'll see that a lot of times the predicted red dashes are right on top of the actual true value. Although sometimes they kind of go off in the wrong direction. For example, query 9 gives us some really poor results. It's even worse than the optimizer. But in every other case, it's at least as good as the optimizer. Again, there's another one, query 11. So 9 and 11. The rest of these seem to work pretty well. So what did we learn? The papers really didn't give us much guidance on how to implement this, so we took a few stabs ourselves. The neural network outperformed the query optimizer almost every time, and it approached optimal very often. Still though, there were times that the complicated cases kind of caused a little bit of confusion, especially around the decision point, and it maybe missed the decision point and kept going. And it's a little bit cumbersome to find the optimal. You have to give it every combination of values in a query, every way that it could be run, and then take the results of what it predicts and find the lowest. It would be better if you could just give it the particular query and it tells you what the fastest combination is, perhaps in a reinforcement learning approach. While this model shows that there is a place for AI, we still have questions. Is this fast enough? Is the time it takes to train a problem? And where does the training data live? And finally, is there a better model we could use? Well, that's it, and thanks for watching. I hope you enjoyed the presentation.